Pleasure to introduce our next speaker, Konstantin Fedorovskiy from Moscow State and, more importantly, St. Petersburg State University. He will talk about 3 problems on univalent functions and model spaces. Welcome.
Okay, thank you very much, Ilya. Thank you for the introduction. And of course, I would like to start thanking organizers for making all this program on on spaces of analytic functions, and especially for making the special event related to model spaces. Well, of course, all of us, I hope, have hoped that this event will be not online, but unfortunately, the situation not allowed us to come and to stay together in the same place. Well, but it's more important to keep the contacts, to keep our programs. So it's my great thanks to organizers for making this. Well, I will speak about univalent functions in model spaces. Well, at the first glance, this question seems quite unexpected, because where is model spaces and where is univalent conditions? These two guys seems very far from one to another, but it turns out that there are very good, very interesting relations between these topics, and of course I will start explaining why the questions about univalence in model spaces are of interest. And I start with the concept of so-called nonlinear domains, which were introduced approximately 30 years ago by myself and my colleagues John Carmona from Barcelona and Petr Paramona from Moscow, and in connection with uniform approximation by polyanalytic functions. I will explain this subject a bit later. And now let me introduce the definition. A bounded, simply connected domain G in the complex plane is said to be a nonlinear domain or n-domain for brevity if one can find two bounded holomorphic functions in this domain, U and V, such that the following equality, the following representation of the function z bar holds on the boundary almost everywhere in the sense of conformal mappings. What does it mean? It means exactly that the following equality of angular boundary values holds for almost all points zeta in the unit circle, where f is some conformal mapping from the unit disk D onto domain under consideration. We can see here that all functions, this function f and these functions, these two compositions, of course, are bounded holomorphic functions in the unit disk. Therefore, they have almost everywhere angular boundary values, and well, we can ask about this equality. So this representation will be denoted by this calligraphic N, and this is the representation of nonlinear domains. Well, of course, some comments about this definition. First of all, that this concept doesn't depend on the choice of conformal mapping phi. So if this representation holds for some conformal mapping, then of course it holds for any other conformal representation. Also, in view of Luzin-Privalov bound, the unique linear theorem, the quotient U over V is uniquely defined in nonlinear domains. The next interesting observation is that if we're working with Jordan domain with rectifiable boundaries, then this condition calligraphic N, this one, can be understood directly on the boundary in the sense also of angular values. And some simple examples. Of course, every disk is a nonlinear domain, but any domain which is bounded by an ellipse which is not a circle or by any polygonal line is not nonlinear. And one more interesting example of an even linear domain, which is well known in the theory of so-called quadrature domains. It's a Newman's oval, so that a domain bounded by the image of an ellipse with center at the origin under the simple inversion mapping, Z maps to 1 over Z. And it's very important to mention that both functions u and v in the definition of an even linear domain are not assumed to have some extra regularity, for instance, continuity or something else in the closure. So it's just a bounded holomorphic functions in G, and this quality N is satisfied in the sense, almost everywhere, in the sense of conformal mappings, nothing more. Okay, since I already mentioned the role of this concept in polyanalytic polynomial approximation, I spend maybe a few minutes to explain it very briefly. So I recall that polyanalytic function is on an open set in the complex plane is the function which have the form of polynomial in the conjugate variable with holomorphic coefficients. Accordingly, any polyanalytic polynomial have the same form, but the coefficients g0, etc., gn minus 1 should be polynomials in the complex variable. The same polyanalytic rational function is the polyanalytic function whose holomorphic components are rational functions. And we are interested in question to describe compact sets in the complex plane such that every function continuous on this compact set and analytic on its interior can be approximated uniformly on X by analytic polynomials. It's enough for us. This problem is well known since middle of 90s of the previous century, but the main efforts were focused on approximation by polyanalytic rational functions. And the problem on polyanalytic polynomial approximation was much less studied until the following results. Firstly, in 1996, I found necessary and sufficient conditions on a rectifiable simple closed curve. In order that the system of analytic polynomials is dense, I will not formulate this result exactly because it's a particular case of the following theorem, which is presented on this slide. And later on, in collaboration with John Carmona and Petr Paramonov, we was able to find a criteria for uniform approximation by polyanalytic polynomials on so-called characteristic compact sets in the complex plane. I recall that the compact set X is a characteristic compact set if its boundary coincides with the boundary of its so-called polynomial's convex half its head, which is the union of X and all bounded connected components of the complement to X. And the theorem is as follows. If X is a characteristic compact set and n an arbitrary integer greater than 2, then every function continuous on X and n analytic inside can be approximated uniformly on X by n analytic polynomials if and only if every bounded connected component of the complement is not an even linear domain. So this theorem is a starting point to study even linear domains, to understand their properties, etc., etc. Well, and the second point why these domains are of interest is, of course, the relations between our representation of the function z bar in the boundary mentioned in the definition. It's relations with the concept of so-called Schwarz function of an analytic curve. I recall here the definition. So if you have some analytic curve, then it's readily verified that one can find a function f holomorphic in some neighborhood of gamma such that our curve is exactly the set of points in this neighborhood where this equation, this condition is satisfied. And of course, any Jordan domain with analytic boundary is even linear if and only if the Schwarz function is meromorphic. Also possible to prove that in this situation, the function more slowly. Okay.
Yes. Okay. Thank you.
Okay. Well, and it's possible to show that the Schwarz function also of analytic boundary of a Jordan domain is meromorphic if and only if this domain is an image of the unit disk under mapping by some rational univalent function, of course, having poles outside the closure of the disk. Well, it's not difficult to check these two properties. And also in this relation, we have the following rigidity property of nonlinear domains. Assume that we are able to find some planar algebraic curve which intersect the boundary of our nonlinear domain by some arc of positive harmonic measure. Then all this boundary is a subset of this algebraic curve. So this is the relation between the concept of Schwarz function and our representation of the function z bar. Moment, what's happening? I'm not able to. Okay. Well, and also it's interesting to recall here not only the concept of a Schwarz function, which is given here, but also the concept of a one-sided Schwarz function. So we only need that the function S is defined inside the domain G, may be except of some compact set K and continues up to the boundary. But the representation of the bar is the same. And it was proved in 91 by Makoto Sakai that if some domain G admits a one-sided Schwarz function, then its boundary is a finite union of analytic arcs. And moreover, it's possible to understand, to find also in his work, in the work by Sakai, that this boundary may have only double points and inward pointing cusps as singularities. Okay? Well, and let me recall that this concept of one-sided Schwarz function also is a bridge between this theorem and the theory of quadrature domains. What is the quadrature domain? It's a domain in the complex plane such that one can find a distribution T with support lying strictly inside G, such that the following representation holds for every holomorphic or harmonic and integrable function in G. It's of course, if this distribution has finite support, so if it's just a sum of values of our function h in some points or its derivatives, then it's usually called the quadrature domain in a classical sense. And any domain possessing this property has a one-sided Schwarz function. For example, a domain which I called Newman's oval and which I mentioned in the previous slides. So the image of an ellipse under the inversion with respect to the origin is the domain of this type. And here in the Newman's oval, this T here, this T F, it's just the sum of in 2 points, Z1 and 2 is in G. So here we have a so-called very, very simple quadrature identity of this type. Okay. Well, and more or less, this is the very brief description of the picture why we are interested in these domains. And of course, the question, for example, is one of the possible questions is how far one can get from analytic curves or piecewise analytic curves when we consider the concept of an univalent domain, thinking our representation of the bar in the form U over V as a generalization of a one-sided Schwarz function. Okay, and in order to state our questions, of course, we need to make another bridge. We need to make a bridge from nonlinear domains to model spaces, and this bridge is very classical. The first building block of this bridge is, of course, the concept of a pseudo-continuation. It can be even readily proved that a bounded simply connected domain is never linear domain if and only if the conformal mapping phi from the unit disk onto G admits a pseudo-continuation. Here there is the definition. So one can find two functions, bounded and holomorphic, outside the unit disk, such that for almost all points in the unit circle, we have this equality also considered in the sense of angular boundary values. But it's important that here there are no complex conjugation. Oh, well, just from this property, one can derive two very simple results. The first one, if we have any one linear domain, and if G is a univalent rational functions with poles outside this domain, then this mapping preserves the nonlinear property. And of course, also possible to derive from this that nonlinear domains have some density property. Namely, in any neighborhood of an arbitrary Jordan curve, one can find an analytic nonlinear contour, so that the boundary of some Jordan nonlinear domain. Okay, so it's really easy, and to prove this, we just need to use the representation of phi bar in our form, in the desired form. And of course, from this pseudo-continuation property, we can obtain the following representation, the following characterization of nonlinear domains. Of course, I am not going to recall what is the model space because this definition sounds today several times. So if G, the theorem is as follows: if G is a nonlinear domain, then one can find an inner function theta such that the conformal mapping belong to this model space K theta. And vice versa, if theta is an arbitrary inner function, and if F is some bounded univalent function belonging to this model space K theta, then the image of the unit disk under this mapping is a nonlinear domain. Well, so the class of all bounded univalent functions belonging to some theta spaces, to some model spaces, coincides with the class of conformal mappings from the unit disk onto nonlinear domains. And we are in the point to understand what class of domains we obtain, what we have. And clearly, we have here several questions. The first one is, of course, to describe such inner functions that the respective model spaces K theta contains bounded univalent functions. From the very beginning, it's not clear what is the situation. The next question, of course, if we have bounded univalent function in some model space, then how large in any reasonable sense, for example, in the sense of dimension, or in some other geometrical, metrical, topological sense, can be the boundary of the image. Moreover, the accessible boundary, I will explain a bit later what and why it's interesting to work with accessible boundaries. And of course, the related question maybe for a first glance looks a bit more particular, but it's also very interesting. Assume that we have a rational univalent function in the unit disk of degree n. By degree of rational function, of course, I mean the maximum of the degrees of numerator and denominator. The function without poles, of course, in the closed disk. Then the question is how fast the length of the boundary of the image. So this integral, of course, this integral, what is this? We consider R of D and take the boundary and take the length of this. So, and we are interested in how fast this length may grow as n tends to infinity. Of course, this problem can be regarded as a quantitative version of the question whether, for example, nonlinear domains with unrectifiable boundaries exist or not. And this is the three main questions, and the last one, which also looks a bit particular, but also of interest. Assume that we have some bounded holomorphic function in the unit disk such that its k degree, for some k, 2, 3, etc., belong to the model, to some model space k theta. And what conditions on f, on theta, on all objects ensure that the initial function f admits observed continuation? Well, this question is also motivated by some approximation problems, namely by approximation properties of rational modulus of this form. You can see that here, if k equal 1, then this is the two analytic or b-analytic functions, but we remove several degrees of the conjugate variable and consider their rational moduli generated by this case power of the conjugate variable. It's also the well-known object in the approximation theory, and in connection with these properties appears this question about taking roots in model space. Well, and we are going to discuss all these problems and well, to present their solutions, because now all these 3, even 4 questions are solved completely. And let me start with a description of model spaces that contains bounded univalent functions. Here I will follow by 2 works. The work by Anton Baranov, Yuri Belov, Sasha Borichev, and myself are in archive, and my paper with Yuri Belov in Russian Mathematical Surveys. Well, also I will not spend time for just recalling the factorization of inner function to the Blaschke product and singular part. It's of course presented here, but what I need to fix the notation. If S is a singular inner function, then by mu S I will denote the respective singular measure on the circle. Well, and of course the Blaschke product B will be this Blaschke product, of course, will be associated with the respective Blaschke sequence. Well, and this is the theorem. Let theta be an inner function in the unit disk, of course, then the space K theta contains bounded univalent functions if and only if one of the following 2 conditions is satisfied. The first one, theta has a 0. It's clear that if theta has a 0, then just a Cauchy kernel, of course, it's a univalent function, belong to the respective model space. It's not a problem. The important question is the case when theta is a singular function. And if theta is a singular inner function, then the condition is as follows. The respective singular measure S is such that that there exists a Berlin-Carlson set in the circle of having this measure positive. And I recall that what is the Berlin-Carlson set, and let me note that this set is firstly appeared as a boundary zero set of holomorphic functions which are smooth up to the boundary. And it's very interesting that this property, the existence of a set, Berlin-Carlson set of mu measure positive, is also a necessary and sufficient condition for the model space Ks to contain mildly smooth functions, for example, the functions from the standard Dirichlet space. This observation, this fact, was proved in, I don't remember exactly, but something like this, by Konstantin Diakonov and Dmitry Havinson. And it's cool, it's interesting that the same condition which ensure the existence of smooth functions also is a condition which ensures the existence of univalent functions. Well, the next is of course the question of how bad, how large the boundaries of nonlinear domain could be. Of course, to answer this question, what we need to do, we need to construct bounded univalent functions belonging to certain model spaces K theta, of course, for some special inner functions theta, possessing some prescribed boundary behavior. Of course, we split this consideration into two parts, of course. The first is the case when theta is a Blaschke product. We can try to find in the spaces KB or in the space Ks, respectively, the univalent functions with some boundary behavior necessary to us. And the first result of this type was obtained by Maxim Mazalov in 1997, Russian mathematician from Smolensk, very interesting work. And he obtained an example of nonlinear domain with nowhere analytic boundary. This example was constructed as a conformal mapping of the unit disk, mapping by the function of this form. Where an is some interpolating Blaschke sequence. Okay, I put here star because I will refer this form of the function several times in what follows. Well, here I recall what is the interpolating Blaschke sequence, and Cn is just some properly chosen sequence of coefficients, and it's important to mention that this sequence of functions is a Riesz basis in the corresponding space KB. What is delicate and difficult in this construction? We need to have this sequence of coefficients Cn from one side, from one point of view. We need to have this coefficient decreasing so fast, then ensure the convergence of this series. At the same time, it needs to decrease not too fast to have some prescribed irregularity up to the boundary. And what kind of univalence condition we can check here? We can play also with these coefficients because the first function here, C1 Z, is of course univalent, and then we also need to play with the sequence Cn in order to keep, for example, the real or imaginary part of derivative positive. This is the univalence condition which works here. Well, the next step is to construct an example of nonlinear domain with boundary of the class C1, but not C1 alpha for any alpha here, of course, any alpha positive. Or this example into versions also was obtained in the following form. But here we need to play more delicate with coefficients Cn, but it's still possible to do. Well, the next example also obtained in the same way by the same construction, but in each next step we need to do more delicate work. Also, it was a result in joint work with Anton Baranov in Sbornik Mathematics. Then we are able to find a univalent function of this form such that its derivative does not belong to any Hardy space HP for p bigger than 1. So the boundary of nonlinear domain could be almost unrectified. Well, the next step is an example of non-rectifier of nonlinear domains with non-rectifiable boundary. It was the first example of this type was constructed by Maxim Mazalov in 2016. The construction is actually the same, but of course we need to do more and more. And let me also mention the example of nonlinear domain such that the Hausdorff dimension of its boundary is bigger than 1. And well, what's happened in the spaces, model spaces generated by singular functions? Of course, if it was already mentioned, if the measure S has atoms, then this then it can be shown that this space, of course, contains bounded univalent functions. For example, this is the case for Pelley-Wiener space. And it was also constructed several particular examples of bounded univalent functions in Pelley-Wiener space. Well, but almost all these examples map. Of course, we are working here not in the disk, but in the upper half plane. It's more convenient. But all these functions map this upper half plane onto domains with quite regular boundaries. Well, and now let me state the next result. In order to do that, I need to recall what is the Hausdorff dimension and the Hausdorff measure of a set. Well, I just recall that for a bounded set, its S-dimensional Hausdorff measure is the quantity defined as follows, where here the infimum is taken over all coverings by our set E by families of disks of radius at most delta. Well, and then we take, of course, limit as delta goes to infinity. So this is the Hausdorff dimension. And by definition, the Hausdorff measure of the order S. And the Hausdorff dimension is the unique number such that for every S less than this number, the Hausdorff measure is infinity. And for every T greater than this, it's equal to 0. It's possible to prove that there exists a unique number with this property. Well, and also for a bounded simply connected domain, I consider its accessible boundary. So it's the set of points in the boundary which are accessible from the domain by some curve. What I mean accessible? I mean that there exists a Jordan curve aligned except its end in G, and it's and belongs to the boundary and equal to our point under consideration. It is not very difficult to show that the accessible boundary is exactly the set f of z, where f is a conformal mapping, f calligraphic is a set of, it's Fa2 set, so the set of all points where angular boundary values exist, angular or radial, and this accessible boundary is exactly the image of all these Fa2 points. Why we need to invite this concept here? When we revert to the definition of nonlinear domain, that's here, we can say that we treat our definition as an equality of angular boundary values of. So this condition and calligraphic and prime fill in some sense only the Fa2 points. So this is the condition only in the accessible boundary. Inaccessible part more or less is invisible for this definition. Thus, it's of course interesting to ask not only the question about how bad, how large the boundary of nonlinear domain could be, but also the question how large its accessible part could be. And what we are able to prove, it's a joint work with Sasha Borichev and Yuri Belov, that for every number beta between 1 and 2, including bounds, there exists a function f also having this form star. So also the function of this form. Which maps the unit disk onto nonlinear domain such that the Hausdorff dimension of its accessible boundary is exactly beta. And moreover, if we consider the complete whole boundary, but not an accessible boundary, but a whole boundary, we are able to find the same function even in the Pelley-Wiener space. So thus we can get very far away from domains with analytic boundaries, considering the nonlinear property, the n property, instead of admitting the Schwarz or one-sided Schwarz function. And of course, now I tell a few words how about, of course, not the proof, but some words about proof of the theorem. The main ingredient is so-called nonlinear needle. What is that? We take two parameters which are actually independent in this construction, and we can construct the function of this form such that, okay, all points wk, all poles, belongs to this segment. This function is univalent in the unit disk and maps it to the following domain. Let me try to, okay, something like this. It's look like a disk with a needle, with a long and very narrow needle. And moreover, this parameter b is in some sense controlled. The b is controlled the size of this needle, while n controlled its length. This nonlinear needle is the main building block for our examples. For example, using this blocks, these needles, and what's important, that we have a good control to the derivative of this function. Okay, this function maps unit disk onto here. No, and of course, I think that I think that this point, the point 1, goes to the base on this needle, and of course we have a good control of the derivative of this function, not of course in the whole unit disk, but it's more important that we have an accurate control of this function in this small disk here. Sorry, I'm not able to draw. Sorry, but I hope you understand. Okay, and this control allow us to add needles to other needles, in some sense to iterate. Well, how to construct using these needles? The example of domain with unrectifiable boundaries. It's a domain looking like this. No, I tried. I will write. Sorry, I will write each needle as a line. Needle of, for example, of the length 1, then the needle of okay, less, etc. So it looks like so looks like a small hedgehog, of course. It looks like a hedgehog domain. So the disk and some and a lot of needles, needles of this type growing. And of course, the mapping function is the sum of these blocks. So it looks like a hedgehog. And well, let me, for a short rest, show this beautiful animal. Perhaps it's more beautiful picture than I tried to draw myself. Okay, and also the control of this derivative of f prime in this small disk, more accurate controls than in the example of domain with unrectifiable boundaries, allow us to construct a needles growing not only from other points in the circle, in the disk, but needles growing from the points which are very close to, sorry, growing to points, okay, I will put from the points which are near to, which lying near to the tip of this needle. So needles on needles. And doing this, we are able to imitate, in some sense, the half par. Of course, let me cut here. We can imitate a so-called H3, for example. Here, this is the continuation of this, of the first needle. Then in the next step, we're growing these two needles. In the next also, here should be some continuation. So we're growing our needles not in the end point, but very close to this. And continuing this this construction, of course, we, for example, arrive to the nonlinear domain with boundary having Hausdorff dimension 2, because this set H3 has dimension 2. Well, and I have approximately five minutes, and I will try to explain the answer for the third question and some consequences of this answer. In order to understand how fast the image of the length of the boundary of the image of the disk under a rational univalent function of a fixed degree n grows, of course, I consider the space of this space of functions, of course, normed, having the norm 1. And here this gamma 0 is exactly the exponent of this growing. And the first result, which was able to prove with Anton Baranov, that this exponent, this number gamma 0, lies between 1/2 and the value of b of 1. So the value at 1 of the integral means spectrum for bounded univalent functions. So this inequality, of course, means that this length can grow as this guy, okay, where gamma is between here and here. Well, it was the first step, and in the perhaps I'm not going to recall what is the boundary means spectrum, well, I only recalled some known estimates on this quantity. There is, of course, a conjecture by Carlson and Jones, which remains open that this value is exactly 1/4. And for example, now it's proved that it's greater than 0.23 and less than 0.46. Okay, and but what we was able to prove in with Borichev and Belov, we was able to prove that the growth exponent for our univalent rational functions is exactly 1/2. We have proved the following estimate. So this estimate was proved previously, but we was able to prove the same lower estimate. And this result has an interesting consequence. So we know now that this integral for rational univalent functions grows as n in power 1/2. But the integral mean spectrum for bounded univalent functions is between 0.23 and 0.46. Then the value of this BB of t, this value of integral mean spectrum, cannot be attained in okay, sorry, I will try to answer a bit later, okay? So can it be attained on a class of univalent rational functions? It's a big difference between the problem related with this with this value. Because for integral mean spectrum for univalent not necessarily bounded functions, this value can be attained on a certain class of univalent polynomials. It was proved by Ilgis Kayumov some time ago. But for bounded functions, even the rational univalent functions are not enough. Well, and also let me make perhaps the final historical remark about this estimate, about okay, this one. Well, it's interesting to compare this estimate for the respective estimate for general rational functions, not necessarily univalent. And it was proved by Dolzhenko many years ago in 1978 that for any rational function having no poles in the unit circle, we have the following estimate, where E is any measurable subset of positive measure. And this estimate, of course, is sharp. The equality is attained, for example, in the function z in power n. So this result was proved many years ago, approximately 40 years ago, but it was completely lost for community and remained absolutely unknown in the literature. And moreover, it was reproved several times, even in the case when E is equal to T with different constants. So it was some line of works where even it was proved with some constant, and when this constant improved. Well, but the original result by Dolzhenko completely covered this work. But here, look, the order n for rational functions, and when we go to univalent functions, we have a order n in the power 1/2. Okay, so perhaps I exhaust my time limits. So the question about roots, perhaps I have no time to explain. And thank you very much for your attention, and let me try to answer your questions. Thank you.
Thank you, Konstantin. Let's thank the speaker. So questions, comments? So there is one question in the chat. Can you see it?
I will, a moment, let me try the chat line. Are you able to prove that the bounded univalent functions in a what do you mean BK? B it's a bляшки? Sorry, Joseph.
I think he means Blaschka.
Ah, you mean just a bляшки, да? Yes? Ooh, good question.
Actually, I think it means backward shift space, model space.
Ah, just in okay,
Yeah.
but well, in general, this univalent functions dense. For a first look,
See, if you
I'm
had
not sure. I'm not sure why, because in fact the univalence is you understand the univalence is a very strong condition, and more or less playing in the opposite playing in some sense in the opposite direction than okay. With general, we have a well, if we write even in the space, of course, in the space generated by Bляшки product,
yes.
well, what kind of sequences of coefficients allow us to have a univalent functions? It seems very difficult question, because any reasonable univalence criteria are very very far to be checked in terms of this series and this series convergence, because in all our constructions we use some modifications of univalence, sufficient univalence conditions, such that real or imaginary part of derivatives on the disk or in some half disk, etc., is positive, or some combination of this with symmetry principle, or even in some examples, some situations, we are able to check the univalence just directly considering the image of the circle, so like some kind of argument principle. And it's only sufficient and the only sufficient conditions. If we write some univalence criteria, all these criteria are known. Is in terms of Schwarz derivative, so it's some quotient of second derivative of f and first derivative of f, or something like this. And if you write f as a series, well, how to check? But in order to prove density, well, we need perhaps maybe it's possible to prove by some other way. I don't know, but. From the first glance, we need to have some criteria, some necessary, maybe different, necessary and sufficient, but some conditions working in both directions, which allow us to check whether some sequence of coefficients Cn, I mean here. Generally, it's just a sequence from L2. But if we are able to check conditions which ensure that this sequence is a sequence of coefficients forming univalent functions, perhaps it's possible to do. But for a moment, I don't know how to work with this. Okay.
More questions or comments? Well, if not, let's thank Konstantin again.